This video segment concludes our examination of the direct effects of rising atmospheric carbon dioxide concentrations on biological organisms. Its major points are: number 1, significant shifts in Earth's flora and fauna have accompanied past changes in atmospheric carbon dioxide levels. Number 2, the rise of C4 plants under past low carbon dioxide atmospheres caused a shift in herbivores. Number 3, a wide range of organisms measure the carbon dioxide concentrations of their surroundings. Pathogenic bacteria and fungi use carbon dioxide concentrations to determine their location. Number 5, insects use carbon dioxide concentrations to determine the location of their prey. Rising carbon dioxide levels will interfere with the ability of certain insects to find food. How will plants and organisms that eat them adjust to rising carbon dioxide concentrations in the atmosphere? If history is any guide, significant changes are coming. Major shifts in Earth's flora and fauna have accompanied past changes in atmospheric carbon dioxide levels. For example, carbon dioxide levels were relatively low 8 to 6 million years ago. Low carbon dioxide levels favor the proliferation of plant species with C4 carbon fixation. C4 plants tend to be more nitrogen efficient than C3 plants and have an average carbon to nitrogen ratio of about 50 versus an average carbon to nitrogen ratio of about 30 for C3 plants. In C4 plants, much of the chlorophyll and leaf protein is centralized in bundle sheath cells that have heavy cell walls to prevent the escape of carbon dioxide released during the breakdown of C4 organic acids. These heavy cell walls also protect bundle sheaths from herbivory. In summary, C4 plants have less nitrogen, and its nitrogen is less accessible to herbivores. The proliferation of C4 plants 8 to 6 million years ago thus shifted the nutritional value of the foliage. Some additional background information on isotopes is required to complete this story. As introduced in an earlier segment, a chemical element may have several isotopes that differ in the number of neutrons in their nucleus. For example, the most common form of carbon on Earth is carbon-12, which has 6 neutrons in its nucleus. About 1% of carbon on Earth is carbon-13, which has 7 neutrons in its nucleus and is thus heavier but still stable. The reaction with carbon dioxide via rubisco in C3 plants discriminates more strongly against the heavy isotope of carbon-13, than the reaction via pepcarboxylase in C4 plants, and so C3 plants are more depleted in the heavy isotope than C4 plants. Herbivores preferentially digest organic compounds with the lighter isotope C12 and thereby preferentially release C12 carbon dioxide during respiration. As a result, the carbon that remains to form tooth enamel is more enriched in the heavy isotope C13 than carbon in the diet. Therefore, the ratio of carbon-13 to carbon-12 in tooth enamel of herbivores eating C3 plants averages minus 13 parts per mil, whereas that of herbivores eating C4 plants averages plus 2 parts per mil. Putting everything together, stable isotope data indicates that lower atmospheric carbon dioxide concentrations 8 to 6 million years ago were responsible for a major turnover in mammalian herbivores. The shift in diet from C3 to C4 plants is evident from the abrupt rise in delta C13 values of fossil teeth from this period. The shift in herbivores is evident from the fossil record, where teeth from this period had higher crowns, which are better suited for extensive grinding required to extract nutrients from the bundle sheaths of C4 plants.